Thank you very much for the introduction, and thanks for the invitation to speak here. I'm very happy to be here. I will change gears a little bit and actually speak about black box models, and these are neural networks, even though we just saw they have their flaws. And in fact, I want to address a theoretical question about neural networks that points a little bit in the direction of better trying to understand what they actually can do and what they cannot do. So we know that neural networks have been used on many, many different tasks. It achieved very much, being it from image annotations to game playing to computational chemistry, natural language processing, and whatnot. So there have been lots of success stories, but there have also been some surprises. So if you look deeper into the literature, there are some cases where they just maybe don't work as well, or, for example, in many cases, like going deeper and deeper, as we know, actually works, but in some cases it just doesn't work, or like it is not improving much. And in general, it's just important to actually understand what can and cannot actually my neural network learn. If you want to rely on these models, if you actually want to use them, it may be very important to understand what can they actually do. And this is kind of the question I want to address today. Not in its entirety, because it actually consists of many, many different parts. So essentially, there's three parts to the question. The first one is, what kinds of decision boundaries or functions can this network actually encode? So this is the question of representational power of a neural network. The second question is about the learning dynamics. Since these are non-convex models, I run my stochastic gradient and it ends up in some stationary point. Is this a good model? Is this a bad model? Will I get a different model next time I run it? So what happens there? So basically, how does the model interact with the optimization algorithm? And the third part is generalization. So if I learn my model and it fits my data set really well, what does that actually mean to see new data points? Can I predict that? So these are the three questions we actually need to understand today. I will focus on the first one, so explaining a little bit what kinds of things can and cannot different neural network architectures do. And for that, we look at two specific examples. The first one is the architecture of ResNet. I'll explain what that is. It's a recently popular architecture, and we'll be interested in the question, how narrow can we make these networks and still represent what we want to represent? And the second question will be about neural networks that take graphs as input, so structured data in forms of graphs. And you can think of this question in a toy example, essentially like this decision boundary here. That's going to be our running toy example. We have 2 dimensions, and we're just trying to learn a decision boundary that's a circle. That's a super simple example that would need a function or a neural network, any kind of learning model that can at least represent a circle. So let's start, and let's actually start with a little bit of history. So the question of what kinds of functions or decision boundaries can a neural network encode is actually not a new one. So people have looked at this for many, many years, and there's some classic examples that I want to mention, or classic results. So moreover, this is called a universal approximation theorem. So universal approximation essentially means that my model class can represent any reasonable function. So there's like, essentially reasonable means it has to be continuous and integrable, but think about like anything we would like to learn essentially. So what these results say that if I have a neural network that is just 1 or 2 layers and it is infinitely wide, then I can actually represent any of these reasonable functions. So what does that neural network look like? Essentially, we have the input layer, so every node here is a coordinate. Then each of these green nodes takes a weighted combination of the inputs, applies a nonlinearity, like a sigmoid function, and then the output layer takes a weighted combination of this green layer. And that's the neural network. So this kind of thing actually works to approximate any reasonable function. So that basically answers my questions that neural networks kind of are very powerful models. They can represent anything that we want, essentially. So why am I giving this talk? Why don't we just stop here? That basically answers my question. So this is a plot that you may have seen before, that chart. The thing is that what people currently use for neural network architectures doesn't actually look like the thing on the previous slide. The thing on the previous slide had like 2 layers. It had infinitely many neurons in the middle layer, and nobody uses in practice a network like that, essentially. So what this plot here shows is the ImageNet challenge, and so from right to left, the networks become deeper and deeper. So this is like right is earlier, left is later, and the accuracy. So the bars mean the errors. So the deeper the network went, the better was the accuracy people achieved. So somehow, the short essence of this is that models become deeper, and they are actually pretty narrow, as you see in this picture. So that's essentially what they look like. So what happens if now my model is actually not infinitely wide? And instead, I can make it deeper. So the previous theory doesn't say anything about that. It assumes that my model has to be infinitely wide. And if I take these infinitely wide networks, I stack them on top of each other, I get something deep that still can represent everything. But it's not what we're doing. We're actually restricting the width. So what I want to look at is what happens if we are restricting the width. Thus, steps actually help us to cover that. And indeed, there's some examples of functions where actually deep network is way better to encode them than a shallow and a wide network. So this particular, it's of course a special case. So this particular function here, you'll need a linear number of units in a deep network and actually only with 2. And if you use a shallow network, you need exponentially many units. So that's just one example that shows actually maybe deep networks are pretty powerful. But of course, this says that this particular function you can encode. It doesn't say that you can actually learn anything that you want. It's just that particular thing, and maybe that's not exactly what we're interested in. So do actually deep neural networks, can they really represent all functions? And in addition, if they can, how narrow can we make them? So is there a limited width we need that we can still represent everything that we want? So first, let's look at the case of a network that looks essentially like the previous one. And the only difference is that the green layer, now we essentially have multiple different layers of that green layer, the hidden layer. So each of these gets a linear combination of the input, applies a nonlinearity, a ReLU in this case. So you have this kink function, and then you have the output. So we have a stack of these green layers. I only showed one of them. And now we ask the question, how narrow can we make these green layers? So infinitely wide works, but how narrow can we make them if we can make the network deep to still be able to represent everything? So basically learn every possible decision boundary. So instead of looking at theory, let's start with a toy example. So here's my toy example. Again, we want to learn the circle as a decision boundary. So the input is only 2 dimensions because I have x and y coordinate, that's it. And for the moment, I have 2 dimensions as input, let's use 2 dimensions in the hidden layers. So this is what I learned. This is if I use 1 hidden layer, so 1 green layer. This is if I use 2 green layers. And this is if I use more green layers. So somehow it seems like something is not working. It's kind of okay-ish, but something is not working quite as I would have expected it, right? So the circle is a pretty simple decision boundary, but somehow it's not able to actually, and if I would use 100 layers, it would still look something like that. So of course you may say, well, maybe this is because my training algorithm wasn't right. This is after all non-convex. Maybe there's something about my SGD going wrong or something like that. But maybe there's something else. And in fact, the truth is, it is a theorem that this kind of network where I have 2 input layers and 2 hidden layers cannot actually represent a circle. And this holds not only for 2 and 2. This essentially input dimension D, if you use D with D hidden layers, cannot actually do it. You cannot represent any bounded decision area. So basically, a circle is not possible. And what you actually need, so there's also a lower bound with a theory that says if you use D+1 units in the hidden layers, so if I have input dimension 2, if I use 3, then I can actually do it. So this is actually the theory. So okay, that makes us understand essentially that, okay, we need a minimum width. Input dimension D, we need D+1 width to be able to represent everything. Of course, we need to go a little bit deeper, like 2 layers is not always enough. So that answers the question of so-called fully connected networks, the ones I showed. But then there's many other architectures that people have come up recently. In particular, one thing I want to mention is if we look at this chart again, there's this ResNet architecture that gave sort of the last result of these in 2015. What about these architectures? Does anything change if we change something about the architecture of the neural network? So let's look at this ResNet architecture, and let's try to understand what that actually is. So here's what this looks like. Essentially, you have the same thing as before without that red box. So basically, you have that fully connected network, and then you have this identity mapping next to it. So what this network does is each layer is essentially like this fully connected thing, one hidden green layer, and then the x key plus 1, you add the previous layer to it. So you have a fully connected layer, so that's the nonlinear function, plus just copying over the previous layer. That's all it's doing. So, and then you stack those. So basically what it's doing every time, it's applying its like a fully connected layer, and then it has the identity mapping, meaning it copies over the previous layer. That's also called a skip connection. So that is what ResNet is doing. So now I would like to ask the same question again. How many of these green units do we need? How wide can they be to represent any reasonable function?
K plus 1.
What do you say?
K plus 1.
K plus 1, what is K?
Yeah, if there are like K dimensions in the input row, then you need at least plus 1.
So that is like the one I showed previously, right? So this is basically without this. If I have d input dimensions, I need d plus 1 in the green layer. So now what I'm changing is K is here the layer number. I use the same thing. I have d input dimension, and the only thing I'm changing is I'm adding here, like basically this guy, I'm adding the previous layer. Does it change anything? So d plus 1 is a good guess. D plus 1 should work. Because this thing, I could essentially ignore that part. So d plus 1 should work at least. Question is there any difference?
Maybe lesser because you're using this architecture.
So yeah, that's a good guess. So maybe lesser, but how much lesser? Like
Half, 3/4.
3/4? Okay, any other guesses?
So like the average between the input and output layers, no? So min of the two.
Min of the two. So here actually, because I always copy over the input, this thing always has the same width. So if I have like 10 input dimensions, since I always copy, like I have to be able to add them up, this has to all have width 10, so the output is width 10, and then eventually you can maybe do a 1 unit to like predict a label or something. Single label, yeah. So something, hopefully maybe a bit smaller, but the question is how much smaller. So let's see, let's go back to our toy example. So here's our circle again. So this is 2 input dimensions. And let's try to go a bit smaller. Let's try 1 unit, so 1 green unit in there. And I'm just stacking units like that. So let's see what happens. So 1 hidden layer doesn't work, but 2 hidden layers, it seems so it's a triangle. 3 hidden layers, it's getting some kind of polygon shape, and it's approximating the circle better and better as I go deeper. So hey, that's interesting because I'm only using 1 unit in the middle. So just to remind you, this was the result if I use that fully connected network. So there's a difference, interestingly. So now the question is this random, that just maybe that circle is really good for that network that I generated, or is this something that's actually like more widely used? More general than that, because obviously that's like, maybe it's just a lucky case. So indeed, this is actually more generally true. So indeed, the theorem that I'm going to show you basically says that if you use this ResNet architecture, then even if you're in more than 2 dimensions, then 1 unit in the middle is enough. So basically, all these green layers, you can in principle use 1 unit, and it's good enough. So it's actually independent of the input dimension. So instead of d plus 1, we have 1. So this is what this fairly complicated theorem actually says. All it says is that for any reasonable function, I can find a ResNet where the green layers are only width 1 that can approximate it to arbitrary accuracy. The only thing is I have to go deeper. So basically, the more accurate I make it, the deeper I have to go. So interestingly, this is independent of the input dimension. So somehow that ResNet, that little change that I did, so basically just copying over with that skip connection, seems to have made quite a big difference in the representational power of that network. So there's actually a theoretical distinction, not only empirical, that somehow one is possibly better for a certain task than the other one, between these fully connected networks and the ResNet architecture. And the other thing is you can actually represent the same kind of functions with fewer parameters. Because if you think about it, if you go from D to D plus 1, you have essentially order D square connections, right? Like all possible connections between D and D, essentially. And if you go from D to 1, then you have only D parameters, because there's like only D. So it's actually a more efficient representation as well. So this shows like a theoretical analysis that there is indeed a difference between these two different architectures. So that was just one thing I wanted to show in general about representational power of general neural network architectures. These have been used a lot for image data, for example, to better understand their powers and like their differences. Now I want to switch gears a little bit, and I want to talk about neural networks that take graphs as input. So essentially what the neural network is doing, it's taking that graph, it encodes it into a vector, so it essentially finds an embedding, and then you can do machine learning on that, make predictions. Where is this useful? So there's actually various different ways in which you would like to do prediction with graphs, and neural networks do that. So for example, the graph could be a molecule, and I want to predict what is the toxicity of this molecule, how soluble is it, or something like that. So I'm making a prediction from an entire graph to a label. There's other tasks, so this is a recommender task. This is in particular was an example from Pinterest, where you have, for example, this bipartite graph, and you want to make predictions from nodes to nodes. So what this says is that you have users, and you know which users pinned which items. And given an item that a user pinned, you want to recommend other items that the user may like. So essentially, from an item that you saw, you want to predict other items that the user may like. So you're making predictions from node to node. So you want to essentially have an encoding not only of the entire graph, but also maybe of nodes or neighborhoods. Probably it should be some function of the neighborhood of the node. And then there's other tasks where maybe you want to predict from multiple nodes. So here's another example where this could be a network of drugs and genes. And one example application is that maybe there's two different drugs, and if you take each of them separately, not much side effect will happen. But if you take them simultaneously, then suddenly there's a very bad effect. So that sometimes can happen. So you want to find out for which drugs is this likely to happen, for which pair of drugs. So you're taking now two nodes in the network and trying to predict whether there should be a link, and link meaning here that like basically there's some kind of adverse co-effect happening. Similar thing could be in social networks. You're trying to predict links between people. So we are trying to predict from pairs of nodes to labels. So after all, like looking at, then there's many more applications. There's applications in trying to understand intuitive physics, in parsing, and so on and so forth. There's many applications where you actually want to do learning with graphs. And what we saw is we need representations actually of the nodes in the graph and of the entire graph itself. And these representations should somehow capture information that we have about the node. Like if in that molecule, maybe we know the atom that is there, maybe we have some properties. And it should capture some kind of properties of the neighborhoods of these nodes, or like this connectivity structure of the graph. So we want to encode both of them. So the way a big class of these graph neural networks work is that they try to capture both of this, and they work in the following aggregative style. So here we see a very small graph, and we're trying, essentially what they're doing is they're first learning a representation of each node, and then they're aggregating the representations of all the nodes together into a representation of the entire graph. So basically we find a representation of that middle node by taking information from its neighbors. It could just essentially pool, maybe by averaging, maybe by doing some max pooling of those neighbors, applying some nonlinearities. So that is essentially one layer of the network. Every node pulls information from their neighbors. And then in the next layer, we do this all over again. But now in the next layer, since its neighboring node has already taken information from its neighbors, essentially the red node gets also information about the green nodes. So in the second step, we have information about the two-hop neighborhood. In the third iteration, we have information about the four-hop neighborhood, and so on. So that is how they generally work. So we find some encoding that sort of tells something about the neighborhood structure in the graph and the labels of the neighbors. And then in the end, we basically combine all of these. This could be by averaging, like weighted average that we're learning, or just by concatenating them or so. There's different ways you can do that. So now the question that we ask, or that I actually want to ask two questions, is the following. The first thing is, I have different graphs, and I want to understand what kinds of functions can my network learn. That means essentially, are there any graphs which will actually get the same representation? Because if they do, then all I can do is I can always predict the same label for these two graphs. So ideally, every two possible graphs should be mapped into two different representations. And the second question is that better understanding actually how many layers I would need. So I told you this is like this iterative process, and what people have actually seen empirically is that in graph neural networks, deeper is not always better. So often two-layer networks actually is enough, and if you go deeper, it doesn't work so well anymore. So why is that? So this is in comparison to this ResNet for images, where you just like have some stacked thing like that. So let's try to understand a little bit the answers to these two questions, and maybe we'll start with the second one, and the interaction of the layers. And that essentially, so this looks complicated, think of it the following way. We're trying to understand now how is the representation of a given node, so say that node X, influenced by other nodes in the graph. So that is a little bit about understanding how large is the neighborhood from which we're pulling information. So any given node Y, how much information does it contribute to the representation of the node X? And we can find this out by essentially differentiating the representation with respect to Y, and then just illustrating it here with beautiful colors. That means like red is like the highest and blue is very low. So this basically shows, okay, this is the size of the neighborhood. And now we are looking at the neighborhoods. Do we see any properties of these neighborhoods? And what this says is that these neighborhoods, essentially the neighborhoods over which we are aggregating, the influence that any node has on my node X, that behaves like a random walk distribution in that graph. So what is a random walk distribution, and why is that interesting, potentially? So here's a simple illustration of a random walk in a graph. We take our little network again, and we start at some node, and with equal probability, we choose one of the neighbors and go to that neighbor. And once we have done that, we again choose with equal probability one of that new node's neighbors, and we go there, and so on and so forth. So basically, that way, we are just really doing like a random walk in the graph, randomly choosing where to go. And after some point, we measure what is the probability of having reached that node Y. So we start at node X, and we say after, like, what is the probability of having reached node Y after a given number of steps? And that would be the number of layers in my network. So that's the correspondence. And essentially, that probability is directly related to the influence that Y has on my neighborhood. So that's pretty intuitive. Essentially, that random walk is like the inverse of my aggregation speed. That's how you can understand it. So why could that potentially be interesting? And this could be interesting because there's actually quite a lot known about how these random walks spread in different graphs. And this is not at all equal in different subgraphs. And that is the essential part of it. So if you start, for example, at a node that is in a highly connected area, then after 4 steps, you basically are averaging over a very, very, very large, essentially almost the entire graph, very large neighborhood. Versus if you start at a different node, so that's the guy down here, that's not very well connected, you, after 4 steps, the same 4 steps, your neighborhood is actually tiny. Haven't reached anywhere in the graph. So actually, the size of the neighborhoods and the aggregation you're pooling or possibly averaging over depends a lot on the structure of the graph. And now the number of steps that you would want to take to get a reasonable neighborhood size actually depends on the structure of the graph. So it's not a one-size-fits-all. That's the difference. So in particular, the conjecture would probably be that a very, very tiny neighborhood is not good, and a very, very large neighborhood is not good, because if every node is pooling over the entire graph, then maybe there's not much difference between the node representations of the nodes, so you cannot actually distinguish them very well. So that, let me just show you a few failure cases where like predictions went wrong that sort of support this conjecture. So here's a case where 3 and 4 layer networks actually didn't work well, and the 2 layer network worked well. And you see actually the 3 and 4 layer neighborhoods. So what I'm illustrating here is basically a given node, and I'm just looking how, like plotting the neighborhood that it's pooling over, like how large these neighborhoods become very quickly. So that's something where maybe that is too large. And similarly in this one, it's a little bit smaller, but the neighborhoods are fairly large. And here's some cases where the 2-layer network fails, and the higher, like more deeper networks actually work better. And you see actually in the 2-layer case, that neighborhood is really tiny. It's just 4 nodes. And the other ones are a little bit more reasonable, so this is a different case. So kind of that relates to the thought that actually the depth of the network has a high relation to what structure of the graph it has. So you should actually take both of these into account. Now, of course, I cannot really like look by hand at my graphs and say like, okay, these subgraphs have these structures. But there's, of course, a simple fix to this. And the fix is that essentially you let the network decide. So you basically learn what depth you actually would use. And that depends on the graph that you're seeing. So here comes the graph. Each of these layers is just this neighborhood aggregation. And before you do the actual prediction, you can essentially use more local neighborhoods or more global neighborhoods. And that actually does improve the performance. So this was the first part of my question. How does depth actually relate to the structure of the graph? And the second question I want to ask is, what kinds of graphs can these networks actually distinguish? So of course, it's related to the first thing I talked about, where I said, well, maybe essentially different graphs just get this, or different nodes get the same representation, which is bad. You cannot distinguish them anymore. So how does that, for example, relate to what kinds of aggregation schemes you use? So what, like, do you use averaging for the pooling or something else? So let me first show an upper bound. Hoping that you could distinguish all possible graphs is a little bit very ambitious, because you could essentially then solve possibly the graph isomorphism problem. So instead, the best that these aggregation-based networks can do is as good as a popular graph isomorphism test, which is called the Weiss-Feiler-Riemann test. So that's basically the best they could ever do. And that test is fairly reasonable. There's some known failure cases for specific graphs, but otherwise it's pretty good. And this isomorphism test, what it essentially does is it does also neighborhood aggregations, but it uses hash functions to do that. So nothing is wrong. But now the question is, are all of these graph neural networks actually achieving that? Or are some much worse than that, potentially, in distinguishing different graphs? And the way they differ, essentially, is they all use this kind of architecture of, like, you do aggregation, and then you combine it with a center node, and then you do this over and over again, and later you combine everything. So where they really differ is how they actually do these aggregations. And 2 simple cases could be you use maybe a mean pooling or a max pooling. So take the average of your neighbors' labels, or take a max. And here are 2 simple cases where actually max and mean pooling, even though they're actually pretty widely used, fail. So in this case, what happens is, if you think about each of these colors as a different integer, let's say green is 1, blue is 2, and red is 3. If you do if the blue guy does averaging over its neighborhood, it basically says, oh, half of my neighbors are green and half of my neighbors are red. So it actually cannot really distinguish between the graph that has just 3 nodes and the graph that has 5 nodes. And if you take the max, it's even worse. Like if, say, a red is bigger than green, then, well, here you cannot even distinguish something. Like anything, it's just basically which kind of colors occur in your neighborhood, and that's it. So these pooling schemes actually don't seem to achieve as powerful a distinction as possible. So they cannot even distinguish these fairly simple looking graphs. So what would we need that we can be as powerful as this Weiss-Feiler-Riemann test? And what we need, actually, you can already kind of infer from these examples, is that essentially this guy does apply some function of its neighborhood, and the neighborhood is essentially a multiset, a collection of different labels that can occur multiple times. So I'm looking at functions over these multisets, and I want them to basically map different multisets to different representations, different outputs. So this is essentially what an injective function does. That's the definition of injective. Different inputs are mapped to different outputs. So what I need is that these aggregation and combination functions are injective functions, and also the readout function. So for example, instead of using a max or mean pooling, I could use the sum, and the sum is actually injective. So that's a simple change that actually fixes this. So that's what essentially this theorem says. So now this is a simple criterion that we can use to design better aggregation scheme and design networks that are actually better able to distinguish different graphs, that we don't have these strange failure cases. And the only failure cases you would have then, of course, if it learns the appropriate function, would be the same as the Weiss-Feiler-Lehmann test. So what does this actually look like empirically? Here's a few example results. So this is a bioinformatics data. And the red line is essentially using just injective functions, and the orange and these other lines are using functions that are not injective or weaker. And what you see is that this line actually fits the training data set as well as the purple line here is the Weiss-Feiler-Lehmann kernel. It fits it as well as possible. These other ones don't fit the training data set as well. So basically, if you can distinguish all possible graphs, you can fit the training data very well because you can predict a different label for each of these graphs. And this is just another example. But of course, that everything I said doesn't really say much about the test performance because it's just about what can I distinguish. And maybe I can just distinguish too much. But it turns out that actually the test accuracy also often is the best for these kinds of networks. So it's not only the training accuracy. And the difference now is that this is actually the thing that is potentially also able to distinguish all possible graphs. That's the graph isomorphism test. This is the one that is the learned graph network. They can distinguish the same things, let's say, but this guy can learn similarities and this guy cannot. So being able to learn similarities actually helps you better predict because you may actually want to relate graphs that are similar that the fixed thing cannot actually do. The purpose of that purple thing was really only to distinguish graphs, nothing else. So with that, let me just conclude. So I showed you two different examples of answering a question about that is important when you want to understand what can my model actually do. So in particular, recently popular neural networks. What kinds of functions can my network actually represent? What kinds of inputs can it distinguish? And where may it fail? And this is very important to understand to design better models, or to also understand where may my models actually fail. So thank you very much for your time.
Hi, this is Tetara Ariafar, and I have a question. So how does this whole thing compare to Bayesian optimization? Because at another level, you can use Bayesian optimization to actually learn like how many layers or like how many nodes in each layer is sufficient to learn the structure of the neural net or any other model that you're interested to work in. So how this compares to that?
I see. Yeah, so the question is basically you could have automated schemes that actually learn how deep should your network be, etc., how wide it may be. So that is true. So this work really tries to more like fundamentally and theoretically understand what are the factors that go in there that make affect the representational power of these networks. Versus these other automated schemes, they just do essentially a search. But you could, for example, use these results to better guide your search. So even when you do Bayesian optimization, it's a pretty big search space, it's a pretty complex problem. So actually knowing anything about what may actually be the thing that you want to change is very important. So this can go hand in hand. Oh, yeah, you were more.
I just wanted to know, like, tying in just the talk that we had first, is there any research being done about how do we understand the neural network, like interpretability perspective?
Yeah, so there is a bit of research going into that, and it goes in like to what Cynthia says in like designing more structured architectures. There's basically two branches. One is, as she said, basically trying to mimic black box models and maybe doing local linear approximation, things like that, testing for variable importance in these methods. And the other one is to actually try and design models that are more interpretable from first place. So that's another route to go. So you could tie this possibly with now this kind of analysis and say, you want to make it interpretable, but you also want to make it powerful. How could you combine these two and have something that's actually, like you can understand it and still have power? Yeah, like, so of course this fully connected network per se is not very interpretable. I just like connect everything to everything. You can look at the weights, but probably it's not going to tell you something. There is some work that looks at also visualizing actually neural networks. So there's some other work that looks at actually the weights and like for different inputs, and also like looking at, in particular for computer vision, you have basically, you look at the units and you see what actually activates these units. So that is also kind of like trying to find a post-hoc understanding about what might these units actually represent. So that belongs to the first category of things. There's a variety of things that people are thinking about, which is, I think, very interesting. It kind of ties together with the representational power and trying to understand how do networks actually encode things. All of these are very interesting.
Any other questions?
Hey, I was wondering if, in your intuition, like graph isomorphism problems can, for the most part, be solved in practical cases by neural nets, or if, like, we're going to hit an exponential limit, or if neural nets can do like well enough that we don't actually care about the weird edge cases.
So I can't say like for all cases. Often the data you encounter in practice is different from like theoretical worst cases. That's just a general thing that happens. So you can definitely, and I would say that like for practical matters, these networks can be very good. And basically, like our purpose is to design networks and try to find ones that work for the practical cases. And while understanding that there may be failure cases, but it's good to kind of understand what they may look like. So for these graph isomorphism tests, we know what they actually look like.
There's one more question over here.
Hi, Jason. I'm actually very interested to see the graph neural network and it's how it outperforms in some cases into like compared to traditional neural network. I'm wondering like for social network data is quite intuitive to think about the graph database at the beginning. I'm wondering for like more other structured data set like. For example, it's just a transaction, no, not a transaction, like any observations with features as columns. For those data sets, do we need to first build a graph database at the beginning to be able to use graph neural network to work on those cases?
So if there's no underlying graph and you just have a collection of variables, essentially these architectures assume there's an underlying graph because that's how they do the neighborhood scheme. You could, of course, design like some kind of nearest neighbor graph or so. That worked better than using some other neural network that just goes by other kinds of locality or something else. I don't know. I haven't tried it, frankly.
Thanks.
Great. I think we're going to wrap this up right now. Thank you so much, Stefanie. It was great talk. We're about to take a long break for the poster session and for lunch. And before that, I wanted to have